These are the notes for LT3 in the Newton's Laws unit, and the target reads that we're trying to use the equilibrium rule to predict the change in motion of an object that's acted on by several forces. This is kind of a loaded target just because there's multiple things that have to factor in. And so you could look here, yes, we need to predict motion, but in order to do that, we also have to talk about the first law of motion. So a few things are going to come into play here. All right, we have equilibrium rule, and again, the first law is going to be needed. So to get this thing started, look around wherever you're at and find something at rest, like something at rest on a shelf or a table. All right, and in the last target, we know that no matter what that object is, no matter how fancy it is, using a free body diagram, all we need to do is draw a box. So whether it's a stapler, whether it's a remote control, whatever, it's just a box. And we know that if something is at rest and it's sitting on a solid surface, whether a chair, a table, a shelf, whatever, then we know that we have the normal force up, and we have the force of gravity, the weight of the object down. Okay, those are the two major forces. And I'm just going to give it a random number here. So I'm looking at my stapler right now, something really exciting. So let's just say that my desk has to push up with 3 newtons because the stapler's weight is 3 newtons. All right, so there's a free body diagram of that. What we didn't do in the previous targets was give this a name. And we did do this. We said, okay, that means the sum of all forces. In this case, the sum of these forces, because we're going opposite directions, and if it's opposite directions we subtract, is 0 newtons. What we call that is it's an equilibrium, okay, because all of the forces cancel out, and so we know, right, if we did it this way, it's 3 newtons, subtract 3 newtons, 0 newtons. So since they all cancel out, we say it's in balance. That is called the equilibrium rule. Okay, so the equilibrium rule has a couple parts, but what must be true is that all of the forces acting on an object cancel each other out. So the net force has to be 0 if it's the equilibrium rule. But when we have an object at rest, it's called static equilibrium. The word static, think like static cling. You know, a dryer sheet gets stuck to your pants or something when you bring it out. Okay, so static equilibrium is when an object is at rest. Maybe in your ELA class you talk about static characters within a story, characters that never really change. They're constant all the way through. Okay, that's static equilibrium. So if you look around and I see a chair not doing anything, it's just at rest. I see a table at rest. Okay, all of those things are in static equilibrium. But an object could also be in what's called dynamic equilibrium. So back to that ELA class where a character maybe starts out cranky in the story and then something wonderful happens to them and they're the most optimistic, happy person you've ever met by the end. Remember, a dynamic character would change. Well, for physics, dynamic means it's at least moving. And what would happen if something's in dynamic equilibrium? You have an object or a person, whatever. Object moves at a constant velocity. Okay, an object moves at a constant velocity. And remember from quite a while ago now, if something's a constant velocity, that must mean same speed. Okay, so maybe a constant 60 miles an hour, and it must be a straight path. Okay, there can't be any turning. That includes a circle. So same speed, straight path means dynamic equilibrium. So if we think back, all right, let's say that we have a car. All right, let's draw a car. There, everybody's car is in a box. And let's say that this car, so our example is going to be 60 miles per hour, and of course linear. Okay, has to be straight line. So here's our car. Let's think of some forces. Oh, well, let's say that the weight of the car is, I don't have any idea. We could Google it. 30,000 newtons. Well, the road must be able to support the car with a normal force of 30,000 newtons. Okay? Let's say that our car is traveling to the right. Then that must mean our applied force would be directed towards the right. And let's say that that is 10,000 newtons. And if our car is going a constant 60 straight line, then we know that the frictional force that opposes it has to be exactly 10,000. So F frict would be 10,000 newtons. Okay, so look at all those. Well, up and down, we know that 30,000, so if we want to do our sum of all forces here, we would have 30,000 minus 30,000. Okay, so there's 0 with our up and down. And then we have 10,000 subtract 10,000 because they're also going opposite directions. Okay, that's going to equal 0. So the bottom line is the sum of all forces here is still 0 newtons. And we've got all kinds of forces. This car's cruising, okay, but it doesn't matter. So we've got two situations where something's in equilibrium. Okay, one's moving, one is not. All right, what that gets to is this idea of inertia. Okay, the first law of motion, also called the law of inertia, and it helps to predict. It's another explanation for why things do what they do. So AKA, make sure you know, you'll hear it called the law of inertia. So Newton's first law here. Here's what inertia is. If you Google it, it's the tendency to maintain the current state of motion. Okay, so a tendency to maintain your current state of motion. So let's think here. If we've got something at rest, I've got my stapler sitting on my desk. That thing's going to keep doing what it's doing until something comes from the outside. So my hand comes from the outside, because right now my stapler's in static equilibrium. And I don't really want to draw on this. Yeah, I guess I can. Let's just do it here. So here's the stapler. Right, we got 3 newtons each way. Those cancel out. If all of a sudden I pick up the stapler, so I apply a force of 6 newtons, the stapler is going to move to the right. So this would be an outside, okay, which this, another word for that is external. Okay, an outside, and it's going to be unbalanced. So that stapler is no longer in equilibrium because an outside unbalanced force has came and changed it. Now that's going to be harder to do with something that has more mass, right? So more mass, more inertia. Okay, more mass, more inertia. If we take a high school senior guy, some big football player, let's say, all right, and we stand them up next to a little 5-year-old kindergartner, and we want to move them, well, it would be a lot harder to move a big old football player out of your way than a little 5-year-old, right? Because they have more mass. Your tendency to keep doing what you're doing is more if you are more massive. And it would be similar if you're going same speed straight line. Okay? It works the same way if something's in dynamic equilibrium. Okay, because our tendency is rest, if something's at rest, or constant velocity, which is the same speed straight line. You know this. Pretend most of us have sledded down a hill at some point, and so you know that you're going to keep going in the same speed, about straight line. And if somebody runs out in front of you, some unsuspecting little kid, you're probably going right through them, right? It's hard to change motion. An object's tendency is to keep doing what it's doing, and that's what this law of inertia does. Okay, it keeps doing what it's doing. The Steve Spangler video that we watch in class is also on Moodle. So if you should watch that, because we'll reference the egg situation within learning targets. So Steve Spangler, inertia, it's pretty entertaining, and you look at, okay, why is it that that egg is able to do what it does? All right, so that is target 3. It's pretty packed, so don't just jump into a learning target here. Make sure you actually go through all your steps, read through these, watch the videos on Moodle.